Awesome, thank you. All right, hey everyone, welcome to the Ice Giant System seminar series. It's the first one of 2023, super exciting. So some updates. As you all probably realized, we did not require registration for this seminar, and going forward, we won't be requiring registration either. We've got sort of a new system in place. So like I mentioned before, soon we have a new website coming online, so look for some updates there. And then we also have Mallory Kinzik here, who's going to start serving as the co-host. So she'll be running the meetings, most of the meetings kind of going forward from here. But I will obviously still be here. I'll run the listserv, and I'll attend everything and stuff like that. So look forward to those. The listserv, if you haven't gotten on the listserv, let's see if I can find the link. Here we go. You can join the listserv at this website. It's kind of over on the right-hand side, I believe. And this is going to be sort of the main source of communication. And so any Zoom links are going to be sent out through the listserv. Any community updates that are, maybe urgent, everything will be kind of sent out through that listserv. So definitely spread the word about that, get people more involved. And yeah, I'm looking forward to this kind of new version of the Ice Giant System seminar series for 2023. Okay, so I'm going to get into it. So I've got a quick bio to read here. So we've got Dr. Mark Hofstadter, and Dr. Mark Hofstadter received his PhD from the California Institute of Technology and has worked at the Jet Propulsion Laboratory since starting his graduate studies, now for about 35 years. His research focuses on using radio telescopes to study the atmospheres of Saturn, Uranus, and Neptune, as well as the nucleus and coma of comets. Dr. Hofstadter uses both ground and space-based radio telescopes in his work. He is also involved in planning future missions to the outer solar system and is interested in fostering international collaborations. He served as the principal investigator for the microwave instrument on the Rosetta orbiter, or MIRO, which was a small radio telescope that flew on ESA's Rosetta mission. Dr. Hofstadter works with the Goldstone Apple Valley Radio Telescope, or GAVRT, I think is maybe how you pronounce it. Okay. The GAVRT program, which provides opportunities for middle and high school students to carry out real research as part of their curriculum. And today he'll be discussing some of his work on ground-based radio observations of Uranus, which we're all really looking forward to. So thank you so much for joining us. Feel free to share your slides whenever. And I'm going to turn my video off just so that you're kind of the main focus during your talk, but I'll obviously come back for, Q&A. And anyone can feel free to post questions in the chat, or either now or later in the Q&A portion. But yeah, I'll hand it over to Mark now. Thanks so much.
All right, thank you, Jody. Let's see. While I'm sharing here, I will not be able to see the chat, so if there are questions that pop up there, someone else can let me know. I'm happy if you guys interrupt me during the talk with questions. And so please go ahead and you can unmute yourselves to do that. Let's see, I guess that's all. Oh, and then I was going to say, I do think I'll leave plenty of time for questions. And I'm hoping to get some comments and feedback from some of you. All right, so my formal title is The Deep Atmosphere of Uranus, Clues and Mysteries from Ground-Based Radio Observations. And this is work that's part of a decades-long collaboration that has been going on with several people. Brian Butler at NRAO, Alex Aikens and Jim Friedson at JPL. More recently, Ned Moulter and Inka DePatter at Berkeley, Mark Gerwell at the Harvard Smithsonian, and Marzia Parisi, who's also at JPL. So one of the things I love about being an observational astronomer is that sometimes you just get to see things that people don't think should exist. And then you get to wave your hands wildly and speculate what's going on. And that's the fun stuff until someone comes along, a theorist comes along and really puts the details to explain what you're seeing. But so what I'll be doing today is just talking about the observations and the wild speculation part. And as I say, I hope there's plenty of time for discussions that you guys can come up with your own speculations or tell me why some of my ideas aren't right. At the bottom of this screen are two images of Uranus. One on the left is near infrared, one on the right is radio. These are a couple of the nicest images of Uranus at these wavelengths I think exist, and you'll be seeing a lot of them, or you'll be seeing these exact images a lot during my talk. All right, let me open up by, this slide is sort of like my concluding slide, but it's really, what are the mysteries that the radio data have shown us about the planet? So the first one is that there are extremely large spatial variations in probably the composition of Uranus's atmosphere, relatively deep, tens of bars pressure. These are two order of magnitude variations horizontally. And these variations are much stronger than we see, for example, on Jupiter or Saturn for that matter. And so it's an interesting question. Normally, when you see spatial variations, you want to invoke circulation and convective activity, and I will do that. But our typical picture of Uranus is that, oh, it's the boring, sluggish atmosphere without much activity. And yet, here we see that in the deep atmosphere, it seems to have stronger variations than a very active place like Jupiter. So that's kind of that is one of the mysteries. Another one is that the cloud top atmospheric properties seem to be decoupled a bit from what's happening deeper down. And I mean that the zonal winds, the temperature structures we see high up in the atmosphere are different than appear to be, and actually composition is different than we see deeper down. And we'd like to understand why that is. And then these last two things are things I've talked about in the past, but a new result I'll be talking about towards the end of this talk is we now have clear evidence for seeing seasonal changes in the atmosphere at these pressures of tens of bars. And that's deeper than we typically expect seasonal variations to happen, particularly because if the upper and deep atmosphere are decoupled and the seasonal effects of sunlight are all in the upper atmosphere, why is the deeper atmosphere changing significantly? So these are the mysteries that I'll be talking about today. But I wanted to add one other mystery, which was revealed by the radio data, which is the abundances of nitrogen and sulfur on Uranus and Neptune, both the ice giants. The abundances of nitrogen and sulfur relative to hydrogen are way out of whack with what we see on Jupiter and Saturn and in the sun. And so there's this mystery of just the basic composition of the atmosphere. That's something that's been known since 1978. If there's questions about it towards the end, I can go into this, but in the interest of time for this presentation, I'm focused on these other points. And then also I'll speculate and come back to this at the end that it's possible that these changes from Jupiter to Saturn to Uranus and Neptune, and some of these mysteries that I've highlighted here could all be tied to the water abundance of the planet and the fact that as we move outward in the solar system, these bodies may be more water rich. And so we'll come back to that later. All right, and let me first just spend a couple minutes bringing everyone up to speed on what radio observations tell us and why we're interested in doing them. So when we make radio observations, this is just looking at the passive black body emission of the planets. And the amount of energy that the planet emits is controlled by its temperature and composition. And different wavelengths, or longer wavelengths, tend to see deeper into the atmosphere than shorter wavelengths. So by looking at the planet over a range of wavelengths, we get information on the vertical profile of temperature and composition. And by looking over time, we see how that vertical profile of temperature and composition changes temporally. And what's very interesting is now, as of last year, we now have a data set that spans 41 years where we can actually image Uranus and see these spatial variations. And that's half a Uranus Uranian year. So we've now seen all seasons that you can see from the Earth. And this chart I'm showing on the right shows weighting functions, just to give you an idea of where we're sensing in the atmosphere. Let's see, I don't know if you guys can see my cursor, but so it's pressures from 0.1 bar at the top down to a couple hundred bars at the bottom on the vertical axis. And then I'm just plotting horizontally weighting functions. You can see that at a wavelength of about 1 millimeter, that's this blue curve, we're sensing a couple bars temperature. At a wavelength of 1 centimeter, we're seeing sort of the 5 to 20 bar region. That's these red and black weighting functions. And as you go to longer wavelengths, you just see progressively deeper. And finally, at about 20 centimeters, which is the longest image data we have from the ground, you're seeing it down to 50, maybe getting some information about approaching 100 bars. And what I've shown here kind of in a cartoon way is just where we expect various clouds to form. This all just assumes an equilibrium chemical model, which may not work for these planets. But anyway, that's where we sort of expect clouds to be. And so the radio data are probing a very interesting region of the atmosphere. There's a lot of condensation processes going on. There's chemistry going on in this 1 to 100 bar region. And these radio, centimeter to meter wavelength radio observations are the only way we can probe this particular region. Infrared observations are sensing more at the 1 bar level and higher altitudes. Let's see, of course, gravity data does give us some information about this region as well, and I'll talk about that later. Okay, I think that's all I need to say here. And then again, if anyone has any questions or comments, feel free to interrupt me as I'm going.
Yeah, Mark, it looks like there's a question in the chat from Sean.
Okay.
What wavelengths would an orbiter need to use to sense down to the anticipated base of the water cloud, maybe about 300 bar? Yeah,
we'd be wanting to push meter or towards the meter wavelength. And the water cloud, depending on how dense it is, may be dense enough that we cannot see to the cloud base reliably. We don't know because we're not sure how much water there is in the deep atmosphere. But and this is something I'll come back to at the end. I'd love to see a microwave radiometer in orbit of this planet that's able to work at wavelengths approaching 1 meter. That's something we cannot do from the ground. You cannot resolve the planet at those long wavelengths from the ground, and no radio telescope currently even in the planning stages will resolve Uranus at those long wavelengths. All right. I'll go ahead and talk a little bit about the data and what the planet looks like. And so this is an image of Uranus made in 2012. I've highlighted where the North Pole is. The South Pole is kind of on the opposite limb. It's just kind of moved around to the backside of the planet. And the brightness here is just an indicator of how much radio energy is coming off. And you see the pole, in fact, both poles, when you see both poles, but the North Pole is emitting a lot more radio energy than lower latitudes. And that is always the case. Every time we look at Uranus, no matter what the season, these poles, the dominant thing is these poles are much brighter than the rest of the planet. You also see some hints of weaker zonal bands in the data set at at low and mid latitudes, you see them in this image, there's actually structure even in this bright region that are kind of washed out by this stretch. So there are these spatial variations that we can see in the brightness. And then let me also talk about seasonal changes. So as I say, we have data, images of Uranus going back to 1981. And the Earth and the Sun are, when you're at Uranus, Earth and Sun are sort of in the same spot of the sky. So when we look at Uranus from the Earth, we're always looking at the subsolar point. And in the 1980s, it was southern summer, and the south pole of Uranus was basically pointed right at us and the sun. And then over the course of the decades, as Uranus orbited the sun, you see the south pole kind of migrated off towards the left-hand limb, eventually started disappearing. And then you see the north pole beginning to come around. And the equinox, when we were looking straight down at the equator, was in early 2007. And now, as we've passed the equinox, we see the North Pole coming into clearly view. And now we're seeing the North Pole at just about the same season and orientation as we saw 40 some years ago. So we've seen a full half year of Uranus's seasonal cycle, which is enough to sample every season that's visible from the Earth. We cannot see the deep winter, which is on the far side of the planet, at least in the polar regions. But so we have a good idea of what's going on seasonally now. And the data set we have spans many wavelengths, a lot more than is shown here. And we have higher time resolution than is shown here. But this just kind of gives you an idea of the changing viewing geometry of the planet and the changing seasons. Okay. So if there are no questions or comments about this, I will jump right into some of the things we see. All right, let me talk about the spatial variations. This is really just the observation. Well, no, it's more than just the observations. Okay, here's this image of Uranus that I'll talk about a lot. To create these brightness variations that you see, the mid to low latitudes of Uranus have to have 50 to 100 times more opacity than do the poles. This is if these variations are due totally to composition. And that's the only thing that's varying. So temperatures are uniform horizontally. Composition has to vary by this factor of 50 to 100 between pole and equator. That's a lot. And as I say, when you look at Jupiter, you see maybe factors of 2 variations horizontally. If you try to explain these variations using only temperature, to say that, okay, maybe the pole is hotter than the mid-latitudes, you would require, at the few bar level, the poles have to be 5 Kelvin hotter than low latitudes. And as you go deeper, you have to have tens of Kelvin, perhaps as much as 50 Kelvin temperature differences between pole and equator. Those are huge differences to have at depths. Conventional wisdom says temperature variations should get smaller as you go deeper. An example might be the Earth's oceans. When you get to the bottom of the Earth's ocean, at the surface, there's lots of temperature variations in water temperature. At the very depths of the oceans, temperatures are really uniform, less than 2K as you travel all of the world's oceans. And so that's kind of what we expect a deep atmosphere to look like as well. So these huge temperature variations probably are not the way to explain it. And those are the 2 end member explanations, and maybe it's a combination of composition and temperature that explains these features. And I'll talk about that in the next slides. I wanted to mention that the vertical variations are just as strong as the horizontal variations. Again, orders of magnitude variations in opacity vertically as well. That's a little easier to understand because cloud formation and chemistry can destroy or create species that absorb microwave radiation. So the vertical variations are perhaps easier to understand, but there are very strong ones there as well. And then I just wanted to mention this fainter banding that you can see in that image. Those variations, if their composition, are probably on the order of 30%. So more modest variations explain the subtle banding that we see there. Let's see. I think that's all. Oh, I was going to just mention that when you look at the wind field and even the temperature field of the atmosphere at 1 bar and lower pressures, so higher in the altitude, they don't match the patterns and the variations that we're seeing deeper down. And that's just an interesting thing to keep in mind. On Jupiter, there seems to be a better correlation between cloud top winds and the belts and zones that you see visibly, and you will also see at radio wavelengths when you look at Jupiter. At Saturn, there is not a strong correlation between the cloud top features and what radio shows deeper down. And then, as I say, at Uranus and Neptune, it's kind of more like Saturn, where there seems to be a difference between the cloud top conditions or patterns and what's deeper down. All right, time for these speculations. So let me first talk about what could be creating compositional variations across the planet. And this cartoon here is one that I've shown before in various places. It's a cartoon of the atmosphere from about 1 to 100 bars in depth, from the South Pole to the North Pole, left and right. And the density of these blue shading you see is an indicator of or how opaque the atmosphere is. And that's probably tracing the abundance of hydrogen sulfide at altitude, and then ammonia and water as you go deeper. And you see that these equatorial and low and mid latitudes are much more absorbing than the poles. And then there's these smaller scale variations that create the little banding there. Just for reference, I've shown where equilibrium cloud models say various various clouds should form. And it's interesting that it turns out the vertical variations do seem correlated with where we expect clouds to form. So that's an interesting point. All right, so when we first saw this, one of the things we thought was, okay, whoops, there's a large scale equator to pole circulation pattern that might explain this, kind of like a giant Hadley cell on the Earth, but it would have to extend from the equator all the way to the pole. And the idea is there might be this great upwelling at the equatorial and mid latitudes that brings a lot of absorbers from deep in the atmosphere, making that region opaque. As these air parcels rise, condensation processes, the clouds shown on the right, deplete the air parcels of the condensing species, which are also would absorb microwave radiation. And then when the descending air then is very dry, it doesn't contain these species, and it creates these pockets of low opacity over both poles. That's an interesting idea. We've talked about that for a while. Recently, Jim Friedson has been working on a very simple dynamical model where he just forces atmospheric motions by the observed cloud top zonal winds. And interestingly, he does find in most conditions actually, that it creates upwelling at the equator and subsidence over the poles. And sorry, I didn't have time to work very well on the graphics here, but what I've just overlaid on the bottom half of my speculative circulation pattern is a plot of vertical velocities in Jim's model. And so where the curves are positive, the upper half of the graph here, that's regions of upwelling. And when the curve drops below the 0 line, which is about where my cursor is, those are regions of subsidence. And you see that the poles have areas of strong subsidence relative to everywhere else, and the lower latitudes have more upwelling. The detailed pattern does not match exactly what we see here, but it's promising that, okay, maybe there is this sort of large scale circulation pattern that might be able to explain what we see. The thing is, you do really have to maintain these dry, clear regions quite deep in the atmosphere. Whoops, went the wrong way. And so that's something that the dynamicists would have to explain. Okay, so that's invoking large scale circulation. I could also invoke small scale circulation. Instead of worrying about, oh, big equator to pole patterns, what if the low to mid latitudes are just convectively a lot more active? There's a lot of storms popping up and stirring that's going on there. And so locally, that creates a lot of opacity there. And that's why the equatorial regions appear so dark. For this explanation to be correct, you have to strongly inhibit those vertical motions over the poles. And somehow you have to isolate the poles from the low latitudes, because otherwise, even if there's no vertical activity over the poles, bringing absorber up from below, you might expect meridional transport, horizontal flow, to spread the stuff that's coming up at the equator out towards the poles. So you have to isolate the polar regions dynamically from low latitudes. It's kind of creating a huge polar vortex over both poles of Uranus. And I'll defer to a theorist to tell me if that's something possible. So I've talked about large and small scale convective activity to explain this. Let me now talk a little bit about how temperature might explain it. And this ties to what I just said about isolating the poles dynamically. One potential way to do that is with pole to equator temperature gradients that create strong zonal winds and vertical wind shears that kind of isolate the polar regions from the equator. So for this model we're looking at right here, small scale convective activity over the equator explaining this, you probably would want to invoke temperature variations at depth as well to create a zonal wind pattern that could corral all the absorbing species and keep them at low latitudes. All right. Let me look at an end member case where instead of explaining the pole to equator brightness variations with composition, I'm going to try to explain it with pure temperature variations. So here's my cartoon atmosphere again, pressure vertically, latitude horizontally. But now, because I'm assuming composition does not vary with latitude, you see the composition, while it varies vertically, as you go deeper, you get more absorber. Horizontally, things are uniform. And those red temperature numbers just are showing you that there's some temperature profile at the equator. Presumably, it's like an adiabatic temperature profile, and the temperature gets higher as you move deeper. If I try to vary the temperature of the atmosphere to explain the brightness variation seen, what would it have to look like? And again, I'm sorry, I didn't have the time to create a nice visual for this, so I just threw numbers on here. But let me start at the top of the atmosphere near 1 bar level. From Voyager infrared and ground-based data, we know that the equator and the poles near 1 bar are at about the same temperature. At mid-latitudes, say 30 to 40, 20 to 40 degrees, there's a slight temperature minimum when you look at 1 bar. So all this is from infrared observations up here. As you go deeper to explain this bright pole, you need the pole in the radio data, you need the poles to be about 5K warmer than the equator. And as you go even deeper, this difference has to approach 50K. Okay, maybe it's 30K, but you need tens of K at depth to explain this bright pole. And then we can't really constrain what's happening deeper down. I want to believe that at some point the temperature becomes uniform again. So these temperature variations this large would imply hugely strong and increasing zonal winds as you go deeper into the atmosphere, which is not typically what we expect should be going on. Most people prefer the interpretation of composition varying, but as I said, there's probably some combination of relatively modest temperature variations as well as circulation and convective activity variations that are creating the patterns that we see. All right. I've waved my hands wildly about a few things here. I want to just mention that there are a few other factors that have to be taken into account when we're trying to figure out which of these ideas might really be correct. First is, at least in the uppermost troposphere, there's not much convective activity on Uranus. This is seen both by it having fewer really high altitude bright cloud features that pop up. These are, Uranus has fewer than Neptune, Jupiter, or Saturn tend to have. But also the Uranian stratosphere is very depleted. So it does not seem to have many hydrocarbons in it, which implies there's not much methane being brought up from the deep atmosphere into the stratosphere. So Uranus is not, at least the uppermost atmosphere does not appear to be very convectively active. Another thing to fold into this story is that Uranus is not releasing internal heat. All the giant planets formed really hot and are releasing lots of heat left over from their formation. I mean, Jupiter, Saturn, and Neptune are. Uranus is not. And one possible explanation for that is that the heat is trapped either in the deep interior or in the deep atmosphere. And this is where water might come into this story. Could the large abundance of water on Uranus inhibit vertical convection? It's because water is much heavier than the hydrogen atmosphere it's in, and it can tend to damp out motions. And water has been proposed, and this damping of vertical motions by water has been proposed to explain the periodic outbursts that we see at Saturn. Every, I forget, 25 years or so, we see a huge outburst of storm activity on Saturn. And the idea is that water on Saturn is inhibiting convection. And so the interior heats up until the point that the really high temperatures just overcome the density gradients, and you have this eruption of water and activity from deep down. Maybe something like that is happening on Uranus. Uranus and Neptune being even richer in water, we believe, than Saturn. Maybe the whole planet gets, activity is damped down on the whole planet while the heat builds up deep in the atmosphere. And then occasionally the planet just erupts in activity when so much heat has been trapped in the interior that it gets so hot that it can overcome the density gradients. And what's really exciting about that is that comparing Uranus and Neptune, Uranus emits almost no internal heat. Neptune emits 10 times as much internal heat as Uranus. And is it that we're seeing Uranus in its quiescent state where the water is inhibiting convection, and we're seeing Neptune in its active state where the interior has heated up enough to overcome the water density gradients and just drives a lot of circulation? Okay, I'm hoping some people more knowledgeable than I will make comments about that. Another thing to factor in and consider is that we see unexpected variations in the ammonia abundance on Jupiter. The Juno spacecraft, which put microwave radiometers into orbit around Jupiter, have shown this. And that's what the graphic on the right, it shows the distribution of ammonia inferred from the data at Jupiter. And so you see, and these variations don't correlate with where we expect clouds to form. So it's a mystery of what created this on Jupiter as well. And so the fact that there are these strong unexpected spatial variations on Jupiter as well as Uranus, you might want to say, hey, maybe it's the same kind of mechanism that's going on. But if that's true, the mechanism is much more effective on Uranus than it is at Jupiter, because these spatial variations you see on Jupiter are a factor of 2, whereas the spatial variations on Uranus are a factor of 10 to 100. And then I'll mention that the Juno team and Tristan Guillot in particular has invoked a theory he calls the mush balls to explain the variations on Jupiter, and that requires vigorous vertical motions. If that mechanism is acting on Uranus, then it implies the deep interior has much more vigorous vertical activity than we see up at the tropopods. Yeah, they're in the uppermost troposphere. All right, I'm getting towards the end of the allotted time. I want to leave time for discussion. Let me talk a little bit about seasonal variations, and then I'll conclude. So I do have something that's totally new to talk about here. This is something that's just come to light in the last few weeks. Back in 2003, we first reported evidence for temporal changes in Uranus's deep atmosphere. All we could see was that somewhere between 1985 and 1994, the brightness patterns on Uranus changed. And we speculated they were seasonal, but all we could say is they were temporal in nature. But now that we have data out to 2022, and here are these images again, note that 2022, the season is very much like it was back in 1985. Now that we've seen just in our latest data sets that the distribution has returned to the pattern it had in 1985. And what happens is there's always this pole to equator brightness variation. I'll talk about composition variations right now. So the poles are always depleted in absorbers compared to low latitudes. But during the time when the pole is fully and continuously illuminated by the sun, so that's the 1985 and the 2022 geometries, at these times, the poles are more absorbing than they are at other times of the year. There is more opacity in the polar regions now than there was in 2005. Or in fact, any time between 1994 and about at least 2007. It's probably composition, so I'll just keep referring to it all as composition. So during the summer months, the poles become more like low latitudes. Something to be explained. I will comment or will add that it is kind of surprising to see seasonal variations as deep as tens of bars. You have sunlight presumably driving these seasonal variations. And the sunlight is deposited maybe down to 5 bars, maybe it gets to 10, but somehow we are seeing these seasonal effects down towards perhaps down to 50 bars. So this getting the poles in constant sunlight seems to either inhibit the convective patterns that are creating these contrasts, or it decreases the temperature gradients between pole and equator. It seems a little weird, though, that the poles are hotter than the equator, and yet when the sunlight is continuously shining on the poles, that temperature contrast would get smaller between poles and equator. So that doesn't quite make sense to me, but again, smarter people may say that really does make sense. Let me see. Maybe that's, oh yeah, I'll just mention here, this chart on the right, it's a difference plot, and if someone wants, I can explain exactly what it all means. But what I'm highlighting here, this is the brightness of Uranus as a function of latitude. I'm just showing one hemisphere. So it's the equator on the right, pole on the left. And what I'm showing here is the brightness pattern of the black and green curves is very different than the pattern in the red and the blue curves. And the red and the blue curves are 1994 to about 2006. And the black and the green curves are 1985 and 2002. All right, I'm gonna open it up. Oh yeah, before I open it up for discussion, I'm not gonna go through this laundry list, but there's a lot of mysteries here, and I don't think we'll be able to resolve any of this without a flagship mission to Uranus. I won't go through the whole laundry list, but basically it's measurements to understand the spatial variations in temperature and composition, the zonal winds, the depth of the zonal winds, the rotation rate, and perhaps getting probe data, giving us a detailed look at an atmospheric profile in one location. But the two things I want to emphasize are the last two bullets. I would love to see a microwave radiometer in orbit around Uranus. Having it there gives us a much better signal to noise ratio, so we could actually look at longitudinal variations on the planet. Everything I've spoken about has sort of been averaged over longitude. Excuse me. Pretty much because we don't have the signal to noise or we have to do that averaging to really understand, get a good signal to noise on the planet. And the main thing that this ties to what Sean asked me first. I'd love to have really long wavelengths on this microwave orbiter so that we can see the deepest atmosphere well into the water cloud, or where we think the water cloud is, because we just can't do that from the ground. And then the other thing that's really important is to get this mission, or hopefully to have this mission arrive while I'm still alive. So that's one of my goals. All right. These conclusions are just tied to the mysteries I opened at the start. Incredibly strong spatial variations in probably composition, but perhaps temperature, are seen in Uranus's atmosphere. The cloud top motions and temperature do not seem well correlated with what's happening deeper in the atmosphere. And we see seasonal changes occurring at depth, much deeper than we would expect, or than conventional wisdom would call for. And somehow in summertime, when the pole is continuously illuminated by the sun, it somehow becomes more like low latitudes. None of these features are understood, and we need the Uranus mission to really help us unravel these mysteries. All right, and with that, I will hopefully open the floor so that someone can explain to me what it is we're seeing. Oops, let me stop sharing.
Awesome. Thank you so much, Mark. Yeah, everyone's throwing up like the clapping emojis and everything. I know it's hard virtually to sort of indicate that, but everyone's clapping. Everyone's clapping. Yeah. Okay. Right. So we can kind of open it up now for discussion. And by the way, Mark, I really like your kind of flagship to-do list. I really appreciate that. Sort of these are the very specific things that that you might need, and especially the last one, definitely sooner would be helpful.
Yep.
Yeah, and so so anyone can use the raise hand feature on Zoom. You can unmute yourself. You can post it in the chat. We've already got a question here in the chat, so I'll go ahead and start there. So Imka says, Mark, any speculations on what next gen VLA and SCA can do?
Yeah, so next gen VLA and the square kilometer array will be able to image Uranus let me go back to sharing. But, whoops, I can't, there we go. But, so we can do a lot at the shorter wavelengths. Go back to my weighting functions with those new observatories coming online. So we're going to get a, let's say down to about 20 centimeters wavelength. So we're going to really get a good handle on, say, the upper 50 bars of the atmosphere from the ground and these new radio observations. The problem is even the square kilometer array will not be able to image Uranus at a meter wavelength. And as Sean asked, we really want to get out to a meter wavelength to get well into the water cloud region, because a lot of people have speculated that these mysteries are tied to the water abundance. So we want to see into the water cloud region, and you need meter wavelengths to do that. And even the SKA will not resolve Uranus at those wavelengths. So ground-based data can do a lot, but for the deepest atmosphere, we want the orbiter there.
Great, thank you. Yeah, and it looks like Sean, you've got your hand raised. Yeah, feel free to unmute.
Hi, Mark. Question, can you go back to your slide that shows the 4 images of taken in radio wavelengths? I think it was like
Is this
yeah. Okay, so let me make sure I'm understanding this. Like for 2022 and 1985, we see a bright yellow area at the poles. So this is either it's probably a combination of what? Warmer air temperature and lower opacity. Is that why that's bright? Am I interpreting that right?
Right, or primarily lower opacity.
Okay.
So that means hydrogen sulfide probably is really depleted over the poles, or perhaps hydrogen sulfide, ammonia, and water are all depleted over the poles.
Okay, because later on you said something about the poles started acting more like the equatorial regions in the summer, and I was a little confused because your graphic showed upwelling in the equatorial regions, which would be higher abundance, right?
Right, and so the equatorial regions always have a much higher abundance than the polar regions. That is true all the time. But what I'm saying is in 1985 and in 2022, the difference between pole and equator is less.
Gotcha. Okay.
And I suspect, I can't say for certain, but I suspect that the change is over the poles. It's that the equatorial latitudes are sort of relatively constant. And the major change is that the polar regions become more opaque in the summertime.
Okay. So it's a relative thing. Okay, I got you.
Yeah.
Also, I wanted to mention, you probably know this from previous discussions, but for the sake of everybody else, there have been some dynamical simulations, some of the ones that I ran a few years ago, that anticipate a polar cyclone of larger size than what we would see on Saturn. And it looks like, I mean, if you want to think about convergence at the pole and downwelling, you would expect cyclonic circulation. And that's at least your data here would support that hypothesis. It's obviously not proof, but it certainly supports it.
Yeah, and now an interesting thing to add on to that is that at Neptune, which looks similar to Uranus, except the polar region is smaller on Neptune than Uranus.
Right, but
So,
still bigger than Saturn, probably.
Still bigger than Saturn. The transition between equator to pole, it happens roughly around 45 degrees latitude on Uranus, and it's closer to 70 degrees latitude on Neptune.
Okay. One last comment was the Keck picture that you showed, which is probably one of my favorites. That is a fascinating equatorial cat's eye-like feature. It kind of reminds me of maybe the plume hotspot region on Jupiter, just north of the equator. And then, of course, you see that sea of convective looking clouds at the poles. Be really neat to see that up close and personal with a mission and see if that is consistent, or I mean, if we could peer below the polar haze cap to see if those cumulus clouds, how seasonal are they, if they're there all year round, or if they fade or whatever. But anyway, that's all I have. Thanks.
Yeah, and I just comment again on these images. You know, I said that there seems to be not or there, for the most part, there is not strong correlation between the cloud top patterns and what we see at depth, but that this transition between polar to more equatorial regions, you know, there is a correlation here. You know, the brightest part of the polar regions is where we have I think what Larry called the popcorn clouds features. You know, clearly the convective nature here at the pole, and this is all, you know, near the 1 or a couple bar level, is much different than at lower latitudes, at least high in the atmosphere, and then perhaps deeper down.
Great, thanks, Mark. Yeah, Ned, you've got your hand raised. Feel free to unmute.
Yeah, thanks, Mark. Really nice talk. I was interested in the Cheng Li et al.'s model for Saturn storms and how you get this inhibition of convection, which eventually becomes unstable, and then you get this burst of convective activity. And in your speculations, and I know this is just a speculation, you had sort of invoked that we might be seeing Uranus in a quiescent state and Neptune in I don't know what you would call it, an agitated state. But I was curious whether the timescales, or whether anybody has come up with a reason why the timescales would be so different, right? Because on Neptune, it seems that at the mid latitudes, the clouds are or like storms are abundant kind of all the time over the last 30 years. And that seems to differ from, you know, a Saturn great storm whose effects are seen over maybe a whole year, Earth year, but much shorter timescale.
Right. Well, my speculation is that unlike Saturn, where the outburst happens localized in latitude, maybe on ice giants that presumably have a lot more water in them than Saturn, maybe on the ice giants, the activity is global. And so that we've got global activity happening on Neptune because it's in this active state. And that when once enough heat is released and the density gradients stifle activity, then we get very little activity at all latitudes, and that's the state we see Uranus in. Did that make sense? And again, I have no idea dynamically if that's a reasonable thing to say, and I'm not aware of anyone having done the calculations to say that if you take Uranus and put a lot of water in it, do you inhibit convection according to the Lee and Ingersoll model? I am not aware of anyone having done that calculation, but I think it should be done.
Yeah, thanks. I agree. I would love to see somebody apply that model more specifically to the ice giants.
Any other questions?
Yeah, looking in the chat, Sean just posted a comment. So it says, perhaps on the ice giants, when you eventually get an outburst of convection, it invokes more disturbances that grow to be global, thinking of Mars's dust storms that can kick off more and more until it becomes global. And then Jim says it's been done by LeConte and by Friedson, both 2017.
Yes, I'm sorry, Jim, I do remember you had done some of that. Do you want to comment on any of the details there?
I would just say that the time scale is probably related to the fact that if you assume water's inhibiting the convection, the water is deep on the order of 50 or 100 bars, let's say, then that kind of controls the time scale. Whereas on Saturn, in the model of Lee and Ingersoll, the condensation of water occurred at a much shallower level, and so timescales were shorter. I think, I don't know, I don't remember if LeConte discussed evolutionary behavior, but in Friedson and Gonzalez, 2017, we looked at the idea of how you would, the timescales to cycle through a convective versus a static sort of atmosphere, and the timescales are on the order of 1 million years.
Yeah.
So, yeah, so it's a long time, and so you can't really expect to see major changes by the time we get a probe in Uranus based on that. But, it's just a theory. So anyway, so yeah, some work has been done on that problem.
Okay. Yeah, and that highlights the desire to study Uranus and Neptune as a pair, particularly if they are the same planet seen in different states, or as some have suggested, and this is something Ravit Hellert often brings up, maybe Uranus and Neptune are just fundamentally different planets.
All right, yeah, we got one more question here from Gordon. Yeah, go ahead and unmute.
Yes, this is kind of the instrument advocacy level. I think probably preaching to the choir, but I think we need both a sub-millimeter instrument and a centimeter wavelength instrument. If you want to use remote sensing to track temperature, you'd probably want to use CO as your basic thermometer. Maybe methane, but probably CO. And you want to be able to measure H2S, which absorbs in the sub-millimeter. And then for the reasons you described, you want these longer wavelengths too. So you kind of have to advocate two types of long wave remote sensing instruments.
Gordy, thank you for that comment. Certainly the sub-millimeter work would really help nail down what's happening in the upper atmosphere. I express my personal bias that I'm kind of more interested in probing the really deep atmosphere, so I tend to think of the longer wavelengths first, but that's maybe just my personal preference.
I bring that up because I think the discussion of instrument complements has sort of been focused towards, an imager and near infrared stuff that would help the satellites. But I think the people that are interested in the deep atmosphere have to kind of push back and say, well, that's fine, but that's not sufficient. We need the long wavelengths too.
Yeah, and I always like to point out a long wavelength radiometer can be used to probe the subsurface of the satellites as well. So there is something you can do with the satellites too there.
Right.
All right, well, we're at the top of the hour now, so I'll sort of close this off. But thank you so much again, Mark. And it was an excellent talk. I'm sure if people have more questions for you, they can reach out to you. Yeah, I will real quick share this this community news slide just in case that's something that people come here for. And I'll also kind of post it in the chat so that you can click on some of these links. The main thing I just want to highlight before people hop off is that let's see here, let me copy paste. There it is. Sorry, it's a little messy. Is just the fact that next month, February 14th, we've got Dr. Kathy Mant from APL giving the next Ice Giant System seminar series. So we're really excited about that. And then there's various other meetings and abstracts and such that are coming up. So feel free to look at those and click on those links I just put in the chat. And so, yeah, with that, I'll sort of close this Zoom out, but thank you all so much for coming, and I'll see you next month. And thanks, Mark.